On July 1st, 2025, astronomers expected to find another drifting space rock. Instead, they discovered Atlas, a fast-moving object from deep space whose blinding brightness and bizarre 5-degree retrograde tilt immediately broke every rule in the astronomy playbook. As the data poured in, leading scientists realized its path was so improbable. The odds were just 0.2% that it arrived here by chance. Why do respected experts now ask if Atlas is a machine, not a rock? If that's true, the implications are staggering, and the next few minutes may change what you think is possible in our solar system. At 2:13 a.m. local time on July 1st, 2025, the Atlas telescope at Rio Hurtado, Chile, registered a new object, catalogued briefly as A11PL3Z, moving against the background stars. Lead astronomer Rafael Diaz and postdoc Olivia Tran were on duty, reviewing the automated alerts that typically flag routine asteroids or distant comets. This signal, though, was anything but routine. The object appeared at 4.5 astronomical units from the Sun, roughly 670 million kilometers out, yet it was already brighter than most inbound comets at that distance. More unusual, its track across the sky defied the patterns Diaz had come to expect. The software's first orbital solution refused to settle. The numbers pointed to a hyperbolic path, not a bound orbit. Tran double-checked the data, then ran a quick simulation. The result: the object was moving too fast, on a trajectory that would never loop back to the Sun. It was coming from deep space, and it would not return. Within 3 hours, the team issued a high-priority anomaly alert. Atlas's automated system flagged the object for immediate international follow-up, pinging observatories from Hawaii to South Africa. Diaz sent a terse message to the internal network. Check this, on a hyperbolic south origin, not an asteroid. Could this be 3I? By sunrise in Chile, telescopes around the globe had confirmed the inbound track. The Minor Planet Center assigned the formal tag C/2025N1 Atlas, and the scientific chatter began to build. This was only the third time in history that astronomers had caught an interstellar object entering the solar system, after Oumuamua in 2017 and Borisov in 2019. Unlike its predecessors, Atlas arrived from a direction almost opposite the solar apex, a region where few had expected to find interstellar debris. Its velocity, a hyperbolic excess of 58 kilometers per second, left no doubt about its origin. The initial orbital fit revealed a retrograde tilt of about 5 degrees from the ecliptic, setting it apart from most known comets and asteroids. The odds of such an alignment, according to later calculation, were just 0.2%. As the international network of telescopes began their observations, some detected a faint coma, a thin, hazy envelope suggesting the object was releasing gas and dust as it neared the sun. That early sign shifted its classification from asteroid candidate to active comet, but the story was already spiraling beyond standard explanations. By midday, NASA's Planetary Defense Coordination Office was debating whether to allocate precious telescope time for this new arrival. Some argued for caution, others pushed for aggressive observation. Diaz and Tran, meanwhile, continued to field calls from journalists and colleagues, trying to balance the excitement of discovery with the need for scientific rigor. Their logbook entries from that day remain clear. If this isn't a rock, it's bigger than a publication bump. For the global astronomy community, ATLAS was now a top priority, an interstellar visitor whose behavior, from the very first sighting, refused to fit the mold. Atlas's arrival triggered a scramble for answers, but the object itself seemed to defy every expectation. As it plunged toward the inner solar system, astronomers expected a slow, steady brightening, typical for comets as sunlight vaporizes surface ice. Instead, Atlas's brightness shot up far faster than standard models predicted. Photometric readings from Hubble and Gemini showed its light curve steepening by nearly a full magnitude in just a few days, a rate rarely seen even among the most volatile comets. The numbers didn't add up. If Atlas were simply reflecting sunlight, its nucleus would have to be enormous, several kilometers across. But surface brightness profiles from JWST revealed a compact, almost point-like core with a faint, truncated halo. The math suggested something even stranger. Either the object was much smaller and somehow producing its own light, or it was cloaked in a cloud of unusually reflective dust. Adding to the puzzle, spectroscopic scans began to pick up an odd chemical fingerprint. Normally, solar heating releases iron and nickel together as cometary dust vaporizes, but in Atlas, only nickel showed up. No iron lines at all. This imbalance is almost unheard of in natural comets, where both metals are forged and mixed in the chaos of star formation. The nickel-rich signal appeared consistently across multiple instruments, from ground-based telescopes to the Hubble Space Telescope. That kind of chemical oddity raised questions about Atlas's origin and what processes could have shaped it. Trajectory analysis only deepened the mystery. Atlas was not just on any inbound path. It was sweeping through the solar system on a retrograde tilt of about 5 degrees, nearly opposite the direction of the planet's orbits. Its orbit lay almost perfectly in the ecliptic plane, a configuration that let it pass close to both Mars and Jupiter within months of discovery. Statisticians at Harvard and Caltech ran the numbers. The odds of a random interstellar object arriving with such a precise alignment and timing came out to just 0.2%. That's about one chance in 500. Most interstellar comets should enter at steep angles, missing the planetary plane entirely. Yet Atlas's path cut straight through the heart of the solar system, threading the needle between planetary orbits as if following a preset route. Every new data point seemed to widen the gap between Atlas and any known comet. The brightness curve was too steep, the spectrum too peculiar, the trajectory too perfect. As astronomers mapped out its future course, they realized that Atlas would make a close approach to Mars, just 0.5 astronomical units away, before swinging past Jupiter's orbit and heading back into interstellar space. Each of these planetary flybys increased the sense of improbability. For some, the mounting anomalies demanded new explanations. If Atlas was a rock, it was the strangest ever seen. If not, then something far more remarkable was streaking through the solar system, hiding in plain sight. Harvard astrophysicist Avi Loeb, along with theorist Eric Caro, began to see a pattern in the mounting anomalies. For them, Atlas wasn't just a statistical outlier, it might be a sign of intent. They published a preprint arguing that the object's rare trajectory, perfect planetary alignments, and strange light behavior fit a framework more familiar to engineers than to geologists. Their proposal, Atlas, could be an artificial probe, one that uses advanced orbital mechanics to navigate the solar system with precision. At the heart of their argument is a maneuver known to spacecraft designers but almost unheard of in nature: the Oberth effect. Normally, a spacecraft speeds up by firing its engines at the closest point to the sun, using gravity to squeeze the most energy out of every drop of fuel. But Loeb and Caro flipped the script. They asked, what if Atlas executed a reverse Oberth maneuver, slowing down instead of speeding up, right at perihelion? In theory, this would allow a craft to change direction or even linger in the inner solar system, all while using the sun's gravity to maximize efficiency. For a rock, this is impossible. For a machine, it's a clever way to hide in plain sight. The math behind such a move is daunting. To pull off a significant velocity change at 1.35 astronomical units, the distance of Atlas's closest approach, would require an enormous burst of energy. Calculations show that altering course by even a few degrees at that speed would demand more thrust than any chemical rocket ever built. Nuclear propulsion, or something even more exotic, would be needed. Yet, when astronomers looked at Atlas's path before and after perihelion, they found no abrupt jumps or unexplained slowdowns. The trajectory matched what gravity and cometary outgassing could produce, at least within the limits of current observation. Still, the timing and geometry of Atlas's journey remain deeply suspicious to some. The object's closest pass to the sun happened during a period when Earth-based telescopes were blinded by solar glare. If a maneuver did occur, it would have been perfectly hidden from view. Loeb and Caro point out that this window of invisibility is itself an unlikely coincidence. They argue that if a probe wanted to mask its activity, it couldn't have picked a better moment. Comparisons to Oumuamua are unavoidable. That first interstellar visitor, detected in 2017, also displayed a hyperbolic orbit and unexplained acceleration, but with no visible gas or dust. Most scientists chalked it up to natural causes, until it was too late to gather more data. With ATLAS, the debate is happening in real time. Theories that once seemed outlandish are now being considered alongside standard models, not because the evidence is overwhelming, but because the odds of so many rare events lining up by chance are vanishingly small. For Loeb and Kiro, the lack of direct proof does not close the case. They argue that when faced with a rare object, on a rare path, doing rare things, science cannot afford to rule out technology. ATLAS may be a rock, but if it's a machine, the implications are profound. The next step is clear: more data, sharper eyes, and a willingness to question what we think we know about visitors from the stars. Hubble's first high-resolution images of ATLAS arrived just days after the object's discovery, and the results sent shockwaves through the astronomy community. Instead of the broad, fan-shaped tail seen on most comets, ATLAS displayed a dense, sharply defined central glow. The core appeared almost point-like, far too compact for the amount of light it was emitting. Surface brightness profiles from both Hubble and Gemini telescopes revealed a steep fall-off, with most of the light packed into a region smaller than a single pixel. If ATLAS was simply reflecting sunlight, its nucleus would need to be several kilometers wide. But the actual measurements suggested something much smaller, possibly just a few hundred meters across, hidden inside a cloud of unusually reflective dust. Adding to the intrigue, photometric readings from JWST and SphereX showed a brightness increase that defied standard comet models. As ATLAS approached the Sun, its light output rose by nearly a full magnitude in just a few days, much faster than the gradual brightening expected from solar heating. This kind of rapid change is rare even among the most volatile comets. The numbers forced astronomers to consider alternatives. Either ATLAS was shrouded in an ultra-efficient dust shell that amplified reflected sunlight, or it was generating its own light, perhaps through an exotic power source. Spectroscopic scans only deepened the puzzle. Observatories detected a rich plume of carbon dioxide and organic molecules, but the standout feature was atomic nickel, present in high abundance, yet with no sign of iron. In cosmic dust, these metals almost always appear together, forged side by side in ancient stars. The persistent absence of iron lines, confirmed across multiple instruments, suggested an unusual chemical process at work. Some theorists pointed to engineered materials, noting that advanced alloys or coatings could, under intense heat, release nickel vapor while suppressing iron, a pattern rarely, if ever, seen in natural objects. As the data poured in, another anomaly surfaced. The dust surrounding Atlas seemed to act as camouflage, scattering light in a way that made the nucleus nearly invisible. Forward-scattering models showed a pronounced sunward glow, with light bending around the object and creating an anti-tail effect. Brightest not away from the sun, but toward it. This behavior, while explainable by rare dust geometries, also fits the idea of a deliberate shroud, masking the true nature of whatever lies at the core. Despite exhaustive monitoring, no gamma-ray pulses or high-energy flares have been detected from Atlas. Every attempt to catch a burst of artificial energy has come up empty. Yet the object's optical glow, its chemical fingerprint, and its improbable path through the solar system continue to fuel speculation. Each measurement adds a new layer to the mystery. If Atlas is a machine, it is hiding its power source well. But if it is a rock, it is one that breaks every rule in the book. David Jewett, one of the world's leading comet experts, has spent decades cataloging the quirks and extremes of icy bodies from the solar system's edge. For Jewett, Atlas's oddities are intriguing but not unprecedented. He points to the object's outgassing, jets of gas and dust released as sunlight strikes volatile ices, as well within the range seen among comets, both local and interstellar. Hubble and James Webb spectra confirm the presence of water ice and carbon dioxide, two of the most common ingredients in cometary chemistry. The steep rise in brightness, while rare, can sometimes result from a concentration of fine dust grains or an unusually volatile rich surface. Jewett's team notes that similar light curves have been recorded in past comets undergoing sudden fragmentation or outbursts, events that can mimic the appearance of self-illumination without any need for exotic explanations. Instrument readings from JWST and ground-based telescopes continue to show a spectrum dominated by ordinary cometary gases, with no sign of manufactured materials or engineered energy sources. The nickel-rich signature, while odd, might reflect the composition of Atlas's birth environment, possibly a star system with different chemistry from our own. As for the object's trajectory, Jewett argues that low probability alignments do happen, especially in a universe teeming with billions of rogue objects. He cautions that extraordinary claims demand extraordinary evidence. Until someone detects a signal, a structure, or a pattern that cannot be explained by any natural process, Atlas remains a comet by default. No radio telescope, including those run by SETI, has detected a whisper of artificial transmission from Atlas. The object's silence across the electromagnetic spectrum stands in contrast to the hype. For the skeptical majority, the puzzle is not whether Atlas is a machine, but how nature continues to surprise even after centuries of watching the skies. During the critical hours of Atlas's closest approach to the sun, A strange silence settled over the global astronomy network. The object slipped behind the solar glare, vanishing from the reach of every ground-based telescope. For nearly 2 days, no observatory on Earth could track its motion or measure its brightness. In that window, any change, whether a subtle course adjustment or a burst of activity, would be invisible to human eyes. Astronomers submitted urgent requests to space-based missions, hoping NASA's Solar Orbiter or the European Space Agency's Stereo spacecraft might catch a glimpse from their unique vantage points. But competing priorities and technical limits meant no dedicated observation was approved. The most sophisticated instruments in orbit were pointed elsewhere, leaving a blind spot at the exact moment when ATLAS could have revealed its true nature. This gap in the data did not go unnoticed. In the weeks that followed, scientists and policymakers debated the consequences of missing such a pivotal event. Some researchers called for new funding to upgrade rapid response capabilities, arguing that the next interstellar visitor might bring answers or threats. Others warned that too much speculation could undermine public trust and scientific credibility. Meanwhile, SETI advocates pressed for more support, framing ATLAS as a reminder that the search for life beyond Earth is not just academic curiosity, but a question with real-world implications. The stakes are not limited to scientific discovery. If ATLAS is a machine, it would mean humanity is no longer alone, an idea that would ripple through every field, from philosophy to national security. If it is natural, its rarity still challenges the boundaries of what we know about the cosmos. Either way, the moment of perihelion remains a hidden chapter, a blank space in the record that forces us to confront how much of the universe remains out of reach. ATLAS has become a catalyst, not just for scientific debate, but for a deeper reckoning with the limits of human perception. On July 1st, 2025, 3I/ATLAS became only the third confirmed interstellar object ever detected. Its 5-degree retrograde tilt and 0.2% alignment odds challenge established models. Hubble and Gemini both recorded unexplained brightness variations, while spectroscopic data revealed a nickel-rich signature rarely seen in natural comets. Avi Loeb and Eric Kerou's published analysis introduced the reverse solar Oberth maneuver theory, arguing that ATLAS's trajectory aligns more with engineered intent than random chance. Yet, as David Jewett and other experts point out, JWST detected water and carbon dioxide, and no artificial radio signals were found. Perihelion observations remain incomplete due to solar glare, leaving critical data missing. Today, the scientific record holds both detailed measurements and unresolved anomalies. Whether ATLAS is a machine or a rock, one fact is clear. It has forced astronomers to question what we truly know about visitors from beyond our solar system.